Hello, my name is Giannetto, and today we're exploring the electric tape lab report. The purpose of this lab was trying to discover how much excess charge is formed on a piece of tape due to friction. We also want to know, is this charge positive or negative? And how many excess electrons does the tape gain or lose? We will be studying inductors and conductors, and how do charged particles react when placed near each other. The core principles of this lab are that charged objects create an electric field at points in space. This electric field can interact with neutral objects. Two charged objects generate a force on one another. This force will either repel or attract, depending on the sign of the charges. We will be using glow script to model the interaction between 2-point charges and gravity. Here's a preview of what our lab results were. The tape repelled a negatively charged pen, which makes it negative as well since they have the same sign. They would repel each other. This glow script model displays that the tape floating in air was floating in space with when the gravity force was equal to the magnitude of the electric force generated by the 2-point charges. The green dot is held in place. The blue dot is free to move. As you can see, we found that the force on the green tape to the blue tape is 2.94 e to the negative 3 newtons. Since it's equal and opposite reactions, these forces are equal on each other. The amount of charge per tape is 9.716 e to the negative 9 uh, coulombs, and the number of excess electrons is 6.07 e to the 10. The equations used to calculate excess electrons were the electric field equation, which is equal to kq over r squared, k being a constant, q being the charge on one piece of tape, and r being the distance between the two pieces of tape. The force of the electric field is very similar. It's kqq over r squared. Again, we are assuming the charges are equal, and that r is the distance between the tape when the tape is floating. And then, of course, we used F gravity, or the force of gravity, which is equal to the mass of one piece of tape times g, which is a constant. How we collected our data, we predicted that since the tape is negatively charged, they would repel each other. The negatively charged tape was attracted towards neutral objects, which again proves it's just negative. We measured and gathered the mass of two separate pieces of tape. We then charged two separate pieces of tape using friction so that they have roughly equal charge. We attached one piece of tape so that it would be hanging in the center and could freely move up and down. We then held another piece of tape below the first, placed it 1 centimeter away, and observed that the tape moved 0.7 meters upwards away from the original piece of tape. The total separation was 1.7 centimeters between the charged objects. We then repeated the experiment to ensure accuracy. Here's our glow script modeling. We modeled the tape as point charges, put them equal distance away from each other, and then used the previous equations in glow script to calculate the E field, different forces, and excess charge. They were then modeled as vectors are the charged objects. The electric force is equal to the gravitational force and magnitude on the hanging tape, or the blue one. Calculating excess charge. We assumed that the tapes have equal charge and they act as point charges. As you can see from the diagrams, the force of electric field is equal to the force of gravity on the hanging tape. Since we know the mass, we can calculate the force of gravity using the equations for Fg. The tape was 20 centimeters long, so it has a mass of 0.2 grams. Since a floating piece of tape is stationary after it rose 0.7 centimeters, we can assume that the downward force of gravity is equal to the upward electric force. By setting Fg equal to the equations for Fe, we can solve for the charge Q on one piece of tape. We then divide the answer by 1.6 e to the negative 19, the charge of an electron. We get the number of excess electrons on one piece. Possible errors include that when the tape is in contact with our hands, they are losing charge even though our skin is an insulator. This is why it's important to touch the tape as little as possible so that we don't lose as much charge and they are as similar as possible for our calculations. Slowly, electrons are transferring over to the object the tape is touching, whether it be our hands or another insulator. The two tapes could have slightly separate charges since our way of charging them was not perfect, and other forces may be acting on the tape that was hanging, such as tension from what it was hanging on. Discussion and conclusion. Negatively charged objects attract neutral and positive objects while repelling other negative ones. Electrons can be stolen from one object to another through friction, and these excess electrons create an electric field centered around the object. Again, charged objects produce an electric field. If you change the charge of electrons and protons were switched, our lab results would not change. Similarly charged objects always repel no matter the sign, so if electrons were positively charged, they would still repel. The magnitude of the two charges is equal on the piece of tape, so it would charge, and it's equal to the charge of a proton is equal to the charge of the electron in magnitude. However, the tape would repel neutral objects instead of being attracted to them if it was positively charged.